Welcome back. Transition matrix. Suppose S equals V1 through Vn and T equals W1 through Wn be two bases. So notice two bases of a finite dimensional vector space which should have the same number of vectors. Note, every vector from S can be expressed uniquely as a linear combination of vectors from T. Likewise, every vector from T can be expressed uniquely as a linear combination of vectors from S. That is, every vector Wj, some j, right? Wj can be written uniquely as a linear combination of vectors from S. That is, there are scalars a1j to anj such that a1j v1 plus a2j v2 all the way to anj vn is wj. So notice that j is kept track of among the coefficients rather, and this 1 represents its coefficient of v1. This 2 represents this number is coefficient of v2 and so on. In other words, the coordinate vector of wj with respect to S is given by these coefficients a1j, a2j until anj. So you get a column vector for every wj with coordinates given by coefficients of v1 through vn. So notice wj on the top, on the left are v1 to vn's. So collect all these column vectors. For w1, you have column vectors with respect to column vector with coordinates with respect to v1 through vn. W2, you have these coordinates with respect to v1 through vn. Wj, we saw just now, so on through, and likewise. So this matrix made up of columns that you obtain as coordinate vectors is called transition matrix. So it's from T to S. You see, every T vector can be written as S vector. So it's going from T to S. T to S. It's denoted P, T to S. Notice the arrow from T to S. So this matrix is called transition matrix. Recall coordinate vectors V. Any V can be written as in a unique fashion as a linear combination of vectors from S. You may also write as vectors from T. So coordinate vector with respect to S is all these x coordinates. With respect to T are these y coordinates. The purpose of transition matrix. You see that transition matrix? From T to S, multiply it to this coordinate vector. Turns out you get this coordinate vector. That's the purpose of transition matrix. Coordinate vector from T gets changed to coordinate vectors in S. How do you find transition matrix in Rn? Rn is column space, n entries. So let S be n vectors, T be n vectors. Make a partition matrix A and B. Why can I make? Because these are columns. So place the S columns first, T columns next. Use elementary row operation to transform to reduced row echelon form. Remember, reduced row echelon form. After you get reduced row echelon form, you see, I am in row space n with n vectors. The only way to, and this is a basis. So its reduced row echelon form is the identity matrix. You should get identity in the first partition. The second one is the transition matrix from T to S. So notice T vectors were here. T to S, that is the second matrix. Okay. So let's look at an example. V are these vectors, V1, V2, V3. That's a basis of R3. And W's are these vectors. Okay? So you want to find the coordinate matrix. You want to check that you get the coordinate vector for S to be coordinate vector from T multiplied to the transition matrix. So a lot of talk here. V is any vector from R3. We need to find its coordinate vector in terms of these vectors. We need to find its coordinate vector in terms of S, that is these vectors. And you want to find the transition matrix and check whether the coordinate vector in terms of S is equal the transition matrix times coordinate vector in terms of T. One thing at a time. Identify the transition matrix. So you want transition matrix from T to S. So S comes first, T comes later. S comes first, T comes later. Okay? S are these vectors, T are these vectors. You're going to use elementary row operations and reduce this to reduced row echelon form. That is IN. Row echelon form will be IN. Well, assuming our calculations are correct, this reduces to IN and this transforms to this matrix. So that is the transition matrix. Now check for V the coordinate vectors.